All right, welcome back, everybody. I was having a little bit of a problem here, but I'm hoping everybody can hear me. The speaker and mic were acting up. Okay, decided to go to the beach here, so I'll make it quick. All right, a couple of announcements. If some of you probably already started the exam, there is one problem. I sent an email that the image is not coming across, and basically it was a problem where you use scientific notation to do a calculation. Well, not to worry, it's number 15. I will give you full credit for that particular problem. In fact, remember, that's true for any assignment. It's been an ongoing issue. Canvas sometimes puts the image out correctly. They tell us what tech support, you got to use Chrome, but here we are. I use Chrome, and occasionally I don't see the image myself. So anyway, if you ever don't see the image, no problem. Just let me know and I'll give you the credit. All right. So what I want to do is, I'll answer some questions about today's exam. What I want to do is kind of go over that activity, because I've been going through some of the responses. And I haven't had a chance to get them all knocked out because there's like 60 of you. Okay, and I got to make sure I do it correctly and fairly and all that. So what I want to do is go over it and then at least give you an idea. And I give you a lot of latitude with respect to grading this one. Okay, so anyway, the question is this. It says, record yourself showing your face, explaining to me in great detail the difference between two measurements. And there are two measurements. The first one is 0.02 centimeters, and the second one is 0.0200 centimeters. Okay, so the first thing to notice about those two numbers, obviously the one on the right has 4 decimal places. And so that's a little bit more accurate. So you keep that in mind, right? So evidently they must have measured that maybe with a laser beam, who knows? And the one on the left, maybe use a tape measure to get that, because the one on the left, you can only go to the 2 decimal places. But the key point is this: both numbers are exact. They're both the same number. The difference is in the accuracy. Whether I give you $500, 500, or versus I give you 500.00, am I not giving you the same amount of money? If it's a 0.00, it's a little more accurate. That's it, right? Okay. Sig figs. The first one has only one sig fig. The zeros up front, the 0.0s are leading zeros as per the rules of sig figs. But if you forgot those 2 questions, ask yourself, is there an integer before those 2 zeros? And the answer is no. So they don't count. They're not significant. They're not significant with respect to accuracy in presenting your data. They're significant with respect to magnitude, because they are significant. That's why I said I wish the term significant was an alternative term rather than, because some students think significant. Why doesn't it doesn't matter? Well, it does. As far as magnitude and as far as accuracy. Second number, obviously the first 2 zeros are leading zeros again. The second 2, you may have forgotten, ask the question. What the rules were, but so ask those 2 questions. Is there an integer in front of those 2 zeros? Yes. Here's a 2. So that's a yes. Is there a decimal point anywhere in those numbers? And yes, there is. Therefore, those 2 zeros or trailing zeros do count here. So we have 3 sig figs. So with respect to accuracy, you can see here that the 1 sig fig is the least accurate. You can only go, it's only going to the 100 place, and it has 1 significant figure. And the next one goes to the 4 decimal place, which is the 10/10,000ths place, and it has 3 sig figs. Okay. Now, clearly explain which digits are significant and which are not. I think we went through that. Only the 2 in the first number is significant, and the 2 and the zeros after the 2 are significant with respect to the second number. Okay. Which measurement is more accurate? Well, obviously the one with the more decimal places in this case is 0.0200. Now, I did state before, I said, okay, when we're dealing with presenting your data, add and subtract has one set of rules, multiply and divide has a different type of rules. I'm not using those rules here. I'm just explaining which is more accurate. This has 4 decimal places. Now, if I was going to add and subtract, if I was going to multiply and divide these two numbers, like let's say I'm multiplying these two numbers or dividing them, then my answer should have no more than 1 sig fig, okay? If I was going to multiply or divide those two numbers. If I was going to add or subtract those two numbers, then my answer should have no more than 2 decimal places, okay? There's the difference there in the mathematical function that you're doing with respect to decimal places and sig figs. And which has the most uncertainty? That's the one that's least accurate, okay? That's 0.02. And are they the same measurement? And the answer is yes. Yes, they're both the same measurement. It's just that one is a lot more accurate than the other, simply because whatever tool they used to measure that, they had a more accurate, more precise tool to utilize. All right, so how are they different? I think I explained that. They're different in that the first one is to the 1/10,000th decimal place. So it's a lot more accurate. And the second one is only to the 100th place. Though they have they're the same number, it's just a matter they differ only in accuracy. All right, now the second one activity was, where are we at? Conversion, it was conversion sheet, okay? And this is the one where you're given the conversion factors, 1 inch is 2.54 centimeters, etc. You also have that information on the shapes table. So here they're asking you to convert units. And we're converting here in this case, let me get my pen here. We are converting, this rock has a mass of 0.0057 pounds, okay? 57 pounds. And we want to know, well, what is that converted to in milligrams, okay? In milligrams. So we write down what we have, what we're given, and then I always write down, you know, obviously not here, but if this is a blank sheet of paper, I always write down the units that I'm going to be looking for, because I'm going to use my conversion factors and set those up properly and keeping track of my units so I can get to my answer. Now, they even tell you here that it is at least a 2-step problem. So that suggests that you need to show at least 2 steps, right? Now, if they didn't have that part, you could hopefully, maybe you can see that these 2 conversion factors, you can convert into 1 conversion factor, and that would have been fine. And no problem, you present that. Okay, because you can see if I multiply just the conversion factors, my grams cancel. All right. And so I got 454,000 milligrams per 1 pound. That's a conversion factor. That's legit. Okay. But they're looking for at least 2 based on the question. So I set it up. My first factor, keeping track of my units, okay, is that I have units of pounds and I need to convert it or get rid of pounds. So obviously my next factor must have the pounds in the denominator. Okay, so I'm going from metric to, from English to metric. And so in this case, I'm going to need this conversion factor up here to get me into the metric system. And that's what I do. And I put my grams on top, because at this point, if I were to just stop the math at this point, my units would be in grams. And guess what? I would be in the metric system. However, I'm looking for milligrams. So I need 1 more factor. And that is given that table I gave you where I broke down all the mass, the volume, and the mass, volume, and length. You know, they're all, you know, meters, grams, and liters, different units, but all the same prefixes, the centi, the deci, the milli, and the micro. I can plug in those prefixes in all of those 3 different measurements. And I know that I have in 1 gram, there are 1,000 milligrams. And I set it up again with grams in the denominator. Why? Because I got grams here and I get rid of it when I do my math. So now I am with my units of milligrams, and that's unit wise. I had not even touched the numbers yet. All I did was just set it up and looked at my units, cancel my units, and now I know it's set up properly. Now I bring out the calculator and I type in 0.0057 times 454 times 1,000. Boom, I got my answer. Okay, now don't forget the sig figs. You got 2 sig figs here to begin with. The 1,000 milligram 1 gram, that's an exact number. So that would not play a factor in your sig figs. The 454 is a measurement. So it could play a factor. Remember, the 454 and the 946 are measurements, and it could be a factor in sig figs. The 2.54 centimeter is exact. Okay, so that would not be a factor in sig figs. So the 454 could be a factor, but guess what? We got 3 sig figs in that. And so I'm multiplying, right? I'm multiplying by a number with 2 sig figs, by a number with 3 sig figs. My answer should have no more than 2 sig figs. Okay, so if this number is, a lot of numbers over here, you want to go to this 2 sig fig position and then round everything up or down, or leave the same or round it up, depending on the rounding rules. Okay. All right. The next one. The question was asked, Janice made 2.54 gallons of punch. Okay. How many cups that is. So in here, we're sticking within the English unit, so we're not really converting. The whole purpose of this exercise is to help you utilize the units and set up the problems, because we're going to be using this technique when we get to the chemical reactions and we start doing calculations there. And like I stated before, you will end up probably with the minimum three conversion factors. So here we're going from gallons to cups. All right. Now you can use that image I gave you where you had the big G and you got 4Q within the big G, and okay, and you got 2 pints, 2 cups in a pint, and 2 pints in a quart. Okay, each one is a conversion factor. So I write down what I'm given. I got to get to the units of cups. So I got to find a factor that gets rid of the gallons. I know that there's 4 quarts in a gallon. Now, again, I could combine all these. However, the problem is telling you it's a 3-step problem at the minimum. So present them with the 3 steps, or, or 4 if you want, depending on whatever you need, but a minimum 3-step based on the question asked. So I write down gallons in the denominator because, again, my gallons cancel, leaving me with quarts. Okay. Then I know from the conversion factor, there are 2 pints in a quart. Again, I write it with quarts in the denominator this time because I want to get rid of my quarts, leaving me with pints, units of pints. That is, if I were to stop the calculation at this point, my units would be in pints. But that's not what I want. I need to go to cups. So I got 1 more conversion factor with 2 cups in a pint. And in this case, my pints cancel, okay, leaving me with units of cups. And there you go. Do the math. All those conversion factors are exact numbers, would not play a factors, but the only thing that is not is the 2.54. That's the measurement. So you should have 3 sig figs. I was asked, well, couldn't I just simply combine all that? 4 times 2 is 8 times 2 is 16 cups over 1 quart, 1 gallon. Okay. And because why? If I take my conversion factors and I just multiply just the factors, okay, I end up with that, right? And wouldn't I, get the same answer if I do that? And so on and so forth. And my answer to you is yes. There's nothing wrong with 1 conversion factor, 16 cups. However, the problem talked about a 3-step, okay? And if the problem doesn't say anything about any number of steps, then that factor is more than sufficient to put in if you need to show your work. But as I stated, I recommend just keeping them all in longhand until you're very comfortable with this, because again, we're going to use it down the road, this technique, when we get to chemical reactions. I can't overemphasize that. Let's see here. I was asked a few questions about this. The thought was that I did not give any information concerning the metric units. I mean, I gave you conversion factors in the English units. I gave you conversion factors in the metric units. That's what that table was, that PDF table that had all the meters and grams, meters, and liters, right? And they were all separate. So, but you can combine them if you don't know, if you need to get, in this example, you need to get from milliliters to microliters. You are in one unit system. The number two, we're in the English units who went to gallons to cups. Well, here we need to go from 1.25 millimeters to microliters, okay? And so right down where we're given, I'm looking for units of microliters. Okay, now the conversion factors that we have here that are, they all have in common is liters. The microliters and the milliliters have in common liters. We know that in 1 liter, there's 1,000 milliliters. I put 1,000 milliliters in the denominator because I want to get rid of milliliters. Okay, so I'm at liters, but I'm not at microliters. But I do know that there are 1 million microliters in 1 liter. So I set up my second factor. Note that the liters here is the common factor, leaving me with units of microliters. Now, when you do this number, don't forget to divide by 1,000. So 1.25 divided by 1,000 times 1 million. Okay. And once you do that, you should end up with 1,250 microliters. So in 1.25 milliliters, there are 1,250 microliters. Keeping the track of your sig figs, because the conversion factors are exact numbers and wouldn't be a factor in sig figs again. I may sound redundant, and I am in the beginning because I want to make sure if I repeat it, it's probably might be information you need, you know? All right. So let's go to the next one. Now in this one, let me clear up here. We are going from English units to metric units, okay? And you're going to have a multiple steps here. And some of them are, again, obvious, all right? But note the question, show at least more than 4. Here I show 1, 2, 3, 4, 5, 6. Some of these obviously you can combine. But anyway, we're going from 17 miles. We want to convert that to kilometers. Okay. So in that table I gave you in the PowerPoint slides, I gave you 1760 yards per mile. Okay. So you can use that to convert me from miles to yards. And I know that there's 3 feet in a yard. That's another conversion factor I can use. It gets rid of yards. I'm in feet. Okay. Now, I'm going from miles to kilometers. So I need a factor that converts me from English, from English to metric. And that's what the middle one here is going to do. It's going to get me out of English and into metric. And so now I'm at 3 feet here per yard. I can use another factor to convert the feet to inches. Why? Because my conversion factor is centimeters per inch. So now I can set it up, put in my 2.54 centimeters per inch. Notice how I'm setting it up, making sure that the units are in the proper position. So when I do the math, they cancel out. Okay. And so then now at this point, I am in centimeters, which puts me in the metric, but they're asking you to get to kilometers. So now I need factors to get me into kilometers. So there is a 1 meter is equal to 100 centimeters. Notice the next two factors, what they have in common is meters, just like the liters had up here when we did the microliters, right? So next factor gets me into meters. Now I'm into meters, but I need to get to kilometers. So I need one more factor, 1 kilometer, there's 1,000 meters, and it's good to go unit wise. I go back and check to make sure that the digits are in the right position. And now it's a matter of you just typing in that number into the calculator. So 17 times 1760 times 3 times 12 times 2.54 divided by 100 divided by 1,000, you end up with 27 kilometers. So 17 miles is equivalent to 27 kilometers. Okay, with 2 sig figs. All right. So any questions about that? Okay, the point here is to set up your conversion factors in such a manner that the units you started off with, that you're starting up with, eventually end up to the units that you want to get to. All right. And then just a matter of setting them up, making sure you put in the number in the right position, because, I've seen examples like, let's take this one, where people will put in, and not thinking about it, would say 12 feet for 1 inch. Okay, as a conversion factor, they inverted this one. But give it some thought. Does that make sense? Of course not, right? 12 feet in 1 inch is not equal to 1 inch. And so, paying attention to detail is important, and not just in your school, but when you get out into work, that's a vital skill set to have in your work position, and make yourself invaluable to your employer because you pay attention to detail. Okay, so learn that skill here so you can take it out there and make the big bucks, okay? All right. So any questions about this? Any questions about this? Huh? Any questions about any other
Yeah,
one?
I got it. I think I kind of already know the answer to this question, but I just wanted to ask you about it, see what you thought. So when you're doing these conversion factors, why? So I noticed what you should do is not worry about sig figs till you're done with all the calculations, right?
That is
Why is that? Like, why wouldn't you look at sig figs after the first one and then do that? Multiply that by the second one. And then...
Yeah, because you propagate the uncertainty, okay, or the error, the potential error, because you may end up, you say you do the first calculation and maybe you boost it up because of your rounding rule. So now you're at a higher number. And then you do the second one, you do the same thing and maybe bring it up in further. So a number, you may end up with a number like 20 and it's really maybe 17. I'm exaggerating, okay, because of the sig fig. So you really don't want to do anything until you're done, with all the math and all the numbers, and then at the end, truncated to where you need to be. So that's a propagation of the error. Just like I said, when you do the rounding, you just look at the immediate. I had some students who were looking like 10 digits down the road and bringing that number up and up and up and forcing this number to go up. Okay. And I'm like, no, just the number that you're there. You change the magnitude by doing it.
Okay.
All right. Good question. Anything else?
On the one where we had to go from, I think it was miles to kilometers. For that one, do we have to always go one step down, like in that particular system that you're in? So like, instead of going from miles to yards, can you just go straight from miles to feet or something like that?
Yeah, exactly. Well, okay. And that is dependent. Now, I don't have a problem to, let me do this. If you were to do all this math here, and you take all these conversion factors, I'll let you do all the math. If you take 1760 multiplied by 12, then by 3 by 12 by 2, let's do it now. Let's do that now. Give me a second here. All right. So I get the 1760. Oh, okay, 1760 times 3 times 12 times 2.54. Okay, 100. Check my numbers. I don't know. Okay, I get 1.60934 for everything there I circle. Does that number look reasonable? Let me double check that. Always double check. So what I'm doing is taking 1760 and multiply by all those numbers within the circle. And so far, if I did my math right, I get 1.609. Which sounds reasonable. If I take that and multiply by 17, I should get close to. Yep, that's what it is. So if I were to take. We'll check here. Everything 1760 times 12 times.
Yeah, so I see. So whenever you input it, if you miss one of those calculations, then it may show up a little bit differently.
Yeah, I
it's
got
intended.
169. So yeah, that number here, if I were to take all these numbers here, I get, one, clear this out. I don't know, my mouse is crazy right now. I got two screens going on, so I'm just like hopping around. Bear with me. Okay, 1.609. I'm just going to take all the numbers and divide it over 1, and that would be kilometers per mile. Okay, and that means if I took all these numbers here, notice the yards cancel, the feet cancel, inches cancel, centimeters cancel, meters cancel, so leaving me with units of kilometers per hour. So there's 1.609 kilometers per 1 mile. That's the conversion factor. Now, I could take that and multiply by 17 and I get that number, okay? And that would be legit. I would take it. But read the question. Okay, the question said, okay, there are many steps here, but it is more than 4. So it's telling you to at least show your work. Okay, which means,
as long as it is a minimum of 5.
5, exactly. Okay, there's more, or even minimum of 4 at least, because it's saying show your work at 4. Like the top one, this is there's more than 1. It's telling you, okay, maybe there's 2. All right. But no, there's no reason why all these conversion factors, even this one here. Okay. That one right there is here is 1,000 microliters in 1 milliliter. Up here. So if I convert all this and divide 1 million divided by 1,000, then I get 1,000 microliters in 1 milliliter. It can be one factor, and that normally would be fine to use. However, again, the question's telling you show at least 1.
Okay.
Show at least more than 1, I should say. Okay.
Very much.
All right, no problem. Good questions. Yeah, all of these can be changed, converted to 1 or 2. But just read the question, see what it tells you. All right, any other questions? Yeah. Okay, if not, I'm gonna go ahead and jump into chapter 4. Don't forget today's exam does shut down at 10. All right, and like I said, question 15, for some reason the image isn't there. Don't freak out. You know, you can, in fact, if you want, no, just don't answer it. You can't answer it because you can't see the image. All right, don't worry about it. When I grade everybody, I'll give everybody the points. All right, now, so first 3 chapters, we kind of introduced chemistry a little bit in the first chapter, and then we got into units here, how to convert and everything, conversions back and forth.
One question. Can
Yeah,
we leave
sure.
the meeting and watch it later? I have a math class at 7.
Yes,
so I
yes,
wanna do
yeah,
it.
of course. Yeah, you're not, it's not, class isn't required. Yeah, I will record it, and obviously, I mean, you have to attend. This is just one part of attending. Attending is doing your homework and, submitting exams. This is for your benefit to help you hopefully understand the content a little better and explain a little, yeah. But yeah,
Okay.
no problem. Yeah.
Okay,
And
thank you.
whenever you have to leave, you just hit the end button. You're good to go.
Okay, thank you.
All right. Because some of these sections, I think they meet like an hour a week. That's it. It's basically on your own time. And that could be challenging sometimes. All right. So let's talk about the atoms. All right. So what this chapter deals with is trying to explain how our current model of an atom, what it consists of, and how we think at this time it's put together. Okay. And it's the fascinating part about this is a lot of this work was beginning like in the 1800s and the early 1900s. And when you think about it, their quote scientific equipment was, not as modern as we got it now, but the power of observation, the power of setting up the good experimentations came up with the model, which to this day exists. This is our current model. It can change tomorrow, until we get more data. But right now, that's not the case. All right, so here we go. 1800s. There's a scientist, Dalton. He proposed what's called the Dalton's atomic theory, okay, about an element. Now, he proposed that an element consists of tiny, indestructible particles called atoms. Now, the concept of the atoms, I may have mentioned this, is not new. The Greeks had it way back when. The concept of elements is not new either. The Greeks also had it, but they only have 4 elements, earth, wind, and fire, and water. That's a good group, earth, wind, and fire. Anyway, he's proposed that an element is made up of tiny, indestructible particles called atoms, but that's not 100% true, because we've learned that these atoms actually break down to subatomic particles. They break down into electrons and protons and neutrons. Okay, so that part didn't fit. They're tiny, yes, for sure, but they're not indestructible. All right. Wait, not too far. Hold on. Second part of his theory was that all atoms of an element are identical, which is true. That part is true. All carbons have 6 protons. That's it. But they do not have the same properties. Obvious example would be carbon in the form of a diamond, or carbon in the form of a dry lubricant. Trying to think of the name of it, but it's a dry lubricant for used for a variety of things, but it's also made of carbon. It's very slimy. Okay, so here we got diamonds made up of carbon situated in a certain manner, which makes them very strong. And then we've got carbons put together in a certain manner, makes them kind of slimy. Okay, so they don't all have the same property. We do know that another part was that the elements, when combined, form what we call compounds. Compounds are made up of two or more different elements. In this example here, you can see we've got two, what looks like diatomic elements, okay, reacting to form two compounds of some sort. It could be anything. Okay. Another aspect about compounds is when these atoms come together to form the formula, the structure of that compound, they come together in whole numbers. Okay, so it's not like they come in half an atom, a 3/4 atom, but it's a whole atom. So the example we show up here is H2O, which tells you that there are 2 hydrogens and 1 oxygen in that structure. A side note here is this, that 99% of the time, the first element that we put when we write the formula tends to be, when we talk about a compound, tends to be the central atom. And then anything else that follows are the elements or the atoms that are bonded to the central atom. The only exception is water. Water we write with H2O. Oxygen is the central atom. So structurally, if I were to draw its formula or structure, I would draw O with a line. That line represents a bond between the hydrogen and the oxygen. Then I would draw another one on the other side. We're going to learn to figure out what kind of structure we can put together using the periodic table and the position of these elements in the periodic table, so we can actually put them together and come up with the structure. Then we're going to use the shapes table to give us a 3-dimensional picture of that compound. But for example, if you have carbon dioxide, okay, notice carbon's first, that's the central atom, and then oxygen is bonded to the central atom, which is carbon. And there's two oxygens per 1 carbon. Okay. All right. Now, we also know that 2 or more elements to form a compound, they can form different compounds. Classic example is carbon monoxide, okay, and carbon dioxide. So here's carbon monoxide. This could be carbon, this could be oxygen, okay, or vice versa. I'm going to be consistent with the other drawing. This is carbon. Carbon and then oxygen, carbon and then oxygen, oxygen, okay? So carbon dioxide meaning 2 oxygens, carbon monoxide meaning 1 oxygen. All right. Now, the model for the atom. It begins, there's my good old buddy here, J.J. Thomson. He lived back in the 1800s, early 1800s, and he is credited, bear in mind we have Dalton now, 1800s, and then toward the end of the 1800s, J.J. comes along, and he is credited with discovering the electron. Unbeknownst to him, based on his work, we wouldn't have television without him. And I'll demonstrate that in a bit, because the equipment that he designed and used to discover the equipment eventually got converted and made into televisions. The old big, the big televisions, the big old heavy ones, not the flat screens we got now. Okay, so what he did was this. He created a particle beam, basically, which he didn't know exactly what it was, but he was able to create a particle beam, and he was able to direct it to a screen that had on it a specific material. Now, keep in mind, that particle beam has high energy. And I said about Mother Nature goes from high to low. Well, it would hit that surface of the screen, transfer that energy to the screen, and that molecule, whatever species is on the screen, would get excited because they absorb that energy, But nature being nature, it's not going to hang out there in the excited state. It goes back down to the what we call the ground state. In the process, conservation of energy dictates that the amount of energy going in must equal the amount of energy going out, either as heat or light. In this case, it releases energy as light, and JJ on the other side sees a image, not an image like you see on your screen now. It's the same thing right now. On your screen now, there's billions of molecules that are being excited. And then after they get back to the ground state, they release light, in this case, color light, just tons of it. And that's what you see, the image here. It's just the result of all these molecules going excited state and ground state, back and forth, back and forth. Anyway, let's look at his YouTube, and we'll take a look at it. Come on.
Cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to...
And this is what I'm talking about. So if you look, it creates these particles, which you're going to learn what they are in a bit. But as these particles travel, they hit the surface of the screen here, transfer the energy, and excite the molecules in the energy. Excite the molecules on the screen, and then they get release that energy and release it as light. Okay, and so this is the precursor of the television, because we're sitting over here on this side watching TV. Okay, watching your cartoons in the old-fashioned television set. All right, let's continue.
The positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube.
Now here's what he did. He applied this field across there. Thing to remember about this is that any charged particle, like an electron, has associated with it, perpendicular to it, a magnetic component. Okay, and that's why we can make electric motors. We got electrical current running through magnets, and we can either create a motor or we can even reverse it and create a generator. Okay, so this particle has a magnetic force to it. Not only that, notice the top side has a negative charge. The top plate has a negative charge, and it's causing that beam to be pushed away from that negative charge. So that indicates that this charge, this particle beam, must have a negative charge. Otherwise, it would not deflect the way it's deflecting.
The cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny...
And then furthermore, like I stated, any charged particle has associated with it a magnetic component, okay? And so that's why if you're running a lot of electrical stuff and it's sensitive information, you want to shield the cable because you don't want the magnetism around its environment to affect that signal. Notice what happens here. You put a magnet, okay, and it deflects that beam.
A magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, Theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge to mass ratio of an electron to be negative 1.7.
Now, obviously, we're not going to talk a lot at all about this mathematics here in the ratio, but the point being here, he was able to determine this ratio of E over M and found that constant, which is negative 1.7 times 10 to the 8th. Okay, which gave him the ability now, knowing E, which is the charge, to determine the mass of that electron. And we'll find out that that mass of electron is extremely tiny. In fact, it's so small that we basically treat it as zero mass. Okay, more on that in a bit.
6 times 10 to the 8th coulombs per gram.
Okay.
A cathode ray.
And so based on good old JJ's work, JJ Thomson, 1904, and keep in mind, it's 1900s. During this time period, there's a lot of stuff going on. He's, you know, we were probably more familiar with Einstein and his work, because this is around the time he's doing his stuff, especially down 1910, 1914. But he's the most well-known scientist, but he's just one of a dozen other scientists who were just as brilliant as Einstein. Okay, so Thomson comes in, he proposes a model for the atom, in which he says that, I don't know, somewhere in there is a positive charge material, and that someplace around the atom are these electrons that are roaming around. Okay, now he's proposing a positive charge. So it's not until another scientist came on board, which a few years later. By the way, his J.J. Thomson's theory, or not theory, or model is called the Plum pudding model. All right, so here comes, we're at 1904, and then we got 1911. Here's another scientist, Ernest Rutherford, also a British scientist. He used the equipment very similar to what JJ did, okay, with the fluorescent screen, but a little bit different. He created some different particles, okay, a different type of beam. It's called alpha particles. We're not going to get involved with that too much, but what he did is he shot these particles through a foil of gold. Okay. Now, if the Plum pudding model was the good model, then what would happen is all this beam, which essentially just go right through the gold. But that's not what he found. He found that some of those particles were being ricocheted off. So suggesting that these beams were hitting something in the gold that was very dense and very, relative to the particle, very big. It's big enough to call it, to have it ricochet off, So let's look at that video.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil.
I'm trying to catch it.
Most of the alpha particles.
I got it. Okay. And so you can see here, we got the particle generator shooting the beam, and the beam going straight through, and this is where the majority of the particles would end up. But if you notice that occasionally you get one that ricochets off over here, some over here, it was going off in different angles. Some of them even going back to the source. And so that kind of very exciting, because there's a different kind of model going on here. He proposed a totally different model. We'll get to that here in a second.
Pass through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, so on the left was Thomson's plum pudding model that would, if it was true, if you will, then Rutherford's work would show that all the particles would basically just shoot through. Okay, but the surprising thing was that Rutherford's work showed that some of these were being ricocheted off, and so what that suggested was that there must be something that these particles are hitting that is pretty dense enough to ricochet these particles away from these atoms. Yes, a lot of them went through, but a lot of them were being ricocheted. So they proposed a different model. Okay, so what Rutherford proposed that in the center is a nucleus, which is a very dense, very heavy nucleus. And he is credited with discovering the proton. All right, so it's the proton / the nucleus. It went not until the 1930s, a few years down the road, that another scientist, Sedgwick, he's credited for discovering the neutron. So we have JJ, the early 1900s. He's got the electron. Rutherford comes in. He's has a proton / nucleus, and then Chadwick comes in, and we have the third subparticle that we are going to talk about, and that's the neutron. And so basically, it's shown that the atom is a lot of empty space between the nucleus. The model you see on the right in the diagram kind of shows what's going on. We have in the center a very dense nucleus, okay? And then we have the electrons orbiting around the nucleus. The electrons are negative charge, the protons have a positive charge, and the neutrons have no charge, okay? And so that's our model. But we do know there's a lot of empty space. In fact, if I were the atom, if I were to put myself in scale, if I was to upgrade the scale of the hydrogen atom, and I represent the nucleus of the hydrogen atom, my electron will be about 3/4 of a mile away. It's quite a bit away, far away distance, but there's that interaction, that nuclear force is very strong, very strong. Hence, we got hydrogen bombs. You can give you an idea how much force is involved in the atom. Okay. Another analogy to give you an idea of the size, if we were to put them in relative size, you can see that if the nucleus was the size of a small marble, and then the cardinal stadium will represent the whole size of the atom. Okay, so very small numbers, 10 to the -13 centimeters in diameter for the nucleus. All righty. So what we have here are the subatomic particles. Okay, and we're only going to worry about the three of them, because guess what? These guys are made up of even smaller particles. All right, and so we're not, it's beyond the scope of Chem 130. So we have the electron, which is denoted by its symbol, which is the lowercase e letter, and has a subscript negative to tell you it's a negative charge. Its location is outside the nucleus, and it has a charge of -1. The relative mass, now what do we mean by AMU? It's a relative mass. To give you an analogy, it would be like, okay, let's say I'm 200 pounds. Okay. Another individual is maybe 400 pounds, big guy. All right. So relative to me, he is twice my weight, right? So I am relative weight 1. He will be relative weight 2. And that's what we've done here, because these weights are so tiny, it'd be difficult numbers to work with. So we give them a relative weight. And the electron is so small that for all intents and purposes, it has a zero mass, but keep in mind, it does have a mass, right? These are the same electrons, electric charge, bad hair day, things like that, running your electronic equipment right now. All right, those are electrons, very small, but very powerful with respect to chemical properties. Then we have the proton that has a P, lowercase p symbol with a superscript plus to denote its positive charge. It is inside the nucleus, has a +1 charge. It has a relative mass of 1. And the neutron has its symbol lowercase n. It has no charge, obviously neutral charge. It is also in the nucleus with the proton, okay? 0 charge. And it also has a relative mass of 1, okay? So the bulk of the atom, the weight of the atom, is made up mostly from the proton and the neutron. Let's see where we at. Okay, let's go ahead and do this. We'll do the slide and we'll stop here because I know some of you, better yet, why don't we just stop it here? Because I know some of you are gonna want to work on your exam and so forth. And let me stop it here. We have slide 4, chapter 4, slide 16. Yeah, let's stop it here and give you time to, if you want to get prepare more for your exam. But I suggest you